Uh, right. So today, what we will do is we will try to build a game. So I think all of you have played this game called Snake, and this is how the game plays. So essentially, this is a mode where we are playing it with a human player, and you can see that the player is either pressing down, up, left, or right to essentially move the snake. The aim is to capture the apple, and whenever you are able to capture the apple will appear in a different place, and the length of the snake will grow. So it will keep on getting taller and taller as it captures more and more apples. So as you can see, it shows you uh, which key on the keyboard is pressed so that to control the movement of the snake. So it goes up, left, again up, then right. So this is how you or I would play this game. Right. So the objective of this class is to, rather than we playing this game, it would be to essentially make the right. So we would like to make the yeah. So we would like to make the computer. We want to teach the computer how to play this game well. So this is what we'll try to do in this particular session. So to break down the objective of this game, so the objective is that we would like to move the snake through a sequence of steps such that we can reach the apple but avoid all the bricks. So we don't want to hit the bricks and somehow meander the snake through so that we are able to reach the apple. So so let us try to break it down exactly what you would like to how would you like to control it. So essentially, if you look at the moves that are available to us, we have four possible moves. We have either left or right or up or down. One moment. The problem is I cannot see the chat, so I don't know if.
So I think we can reserve the questions towards the end. Participants may use the chat towards the end of the session, please.
Or I'll just try to minimize it so that is the screen still visible?
Yes, sir, it's visible.
Okay, awesome. So then I can resize my window so that the chat is also visible.
But the left side is getting cut, sir.
Oh, I see. I see. I see.
Yes, sir.
Okay. So maybe I have to stick to this.
Now it is pretty good, sir. Yes, sir.
Okay. Okay.
Thank you, sir.
So okay. So now the moves that are available to us are left, right, up, and down. These are what we will refer to as actions available to us. So this is a technical term. So whenever there is a nice technical term, I will actually put it down in bold in this blue box. For every possible move that we have, the move will affect the game in a certain way. Like for example, if I take the move left, in that case the snake will move left by one cell. If I move it right, it will move right by one cell, and so on. The next is, so these the effect of these moves are what we will refer to as a transition function. Now uh, so when do we say that we have been able to win the game or we have earned a point? This is when the apple is able to reach the snake is able to reach the apple. What it means is that I would like to take the game to a position such that both the snake and the apple land in the same cell. However, in the process, I would like to avoid all the bricks, right? So essentially, it means that the snake and the brick should never come in the same cell, right? So reaching the apple is a good thing to happen. Hitting the brick is a bad thing to happen. So whenever we want something desirable to happen, then we refer to it as the goal of the game. Whenever we say that something should not happen, we say it is a bad state. I should not get into that particular state. Finally, we would like to prefer a sequence, though I would like to win the game by just reaching the apple. However, I would always prefer the sequence which has the shortest number of steps, right? So given two sequences, the snake can reach the apple. I have a preference. So the preference is given by saying that let us take the sequence of steps which will make me reach the apple the fastest. This is referred to as the cost. And finally, we would like to figure out how do we select this best sequence of steps to reach the apple while avoiding all the bricks. And this is what we refer to as the search problem. So I will sort of define them slightly more carefully, but I hope this is clear to you. So, right. So now let us try to dig down a little deeper and try to understand exactly how do we say that I am not in a bad state, that I have not hit any of the bricks, and or I have reached the apple, right? So we have to figure this out. To do that, the computer must maintain some sort of a data structure. And the data structure that we maintain in this case is something referred to as a state. So in this case, we need to maintain, for instance, the position of the snake. We need to say which cell the snake currently is. We need to maintain the position of the apple. So we need to maintain where the current apple is, and we need to maintain the position of all the bricks. So we need to maintain that which all cells contain a brick. So now how do you say that I have reached a bad cell? However, the position of the snake is same as position of any of the bricks. When do we say that we have reached the goal? When the position of the snake is equal to the position of the apple, right? So this allows us to code it up and say that how do we detect if we are in a bad state or we have been able to reach the goal. So this particular data structure that we maintain, we would refer to as the state of the game. So you can understand that if I give you these three things, it completely describes my game. It completely says that where the snake is, where the apple is, where the brick is. So if I just give you I just give you numerical values of these things, I can actually draw the game canvas. I will be able to cleanly draw what does the game exactly look like at that point in time. Now, formally, now let us define them slightly more clearly. So the first thing we have is what we refer to as the state of my problem. The state of my problem contains all features that I require to describe a situation in this game, to say that what is exactly where the game currently is. The set of all such states is referred to as a state space. Right? The next thing we have to know is there is a sequence of actions. So the action says that what are the different moves the player can do? What are the different steps that I can take to move forward in the search or forward in the game? The next term we defined was something known as a transfer function. So what is a transfer function? A transfer function is a function that takes a state as one parameter, it takes an action as the second parameter, and it gives out a state. So what it does is it essentially says that given some state, if I take some action, which is the next state that I land in. For example, if my current position of my game is such where the snake is here, and the action that I do is to press the left arrow, in that case, the next state that I will end up, given by the transfer function, would be where the snake has moved one position to the left. And finally, we have these nice special states. The first state is referred to as the initial state. This is the state where the game starts. So this is where the bricks were, where the apple is, and where the what is the initial position of my snake. So that will describe my initial state. We will have a set of bad states. So these are all the states where the position of the snake and the position of the brick are at the same place. So whenever I say the position of the snake, I essentially mean the position of the head of the snake, because that is how the snake is moving. So, so what are bad states? Bad states are all states where the head of the snake is in the same cell as any of the bricks. And then we have the goal state. The goal state is the state where I have been able to capture an apple. So the goal state is where the position of the head of the snake is the same as the position of the apple. Now, armed with these descriptions, we would like to now design an algorithm to search the problem, so that instead of a human player, I can have a computer agent which can play the snake game. So the computer agent should be able to move the snake in a manner such that it is able to avoid all the bricks and it is able to reach the apple. So how does a solution to what is a valid solution to the search problem? A valid solution to the search problem is described as a sequence of actions. It's a sequence of actions A0, A1, and so on to say AN, such that every two neighboring actions are connected by a transition, connected by the transition function, which means that if I take the initial state and I take the first action from this, then I move to some state S1. If I take that particular state and I take the second action from this set, then I move to some state F2. If I take the set F2, take the third action, it gives me state S3, and so on, till I reach some state N, such that if I take the last action, I'm able to reach a state SF, such that SF is a state in my goal. Right? So my solution to my game is a sequence of such actions such that each of the neighboring actions are connected by the transition relation. The first, and the final state that you land up with after running this sequence gives me the goal state, or gives me one of the goal states, and and none of the intermediate states, none of the other states that you land in, like S1, S2, S3, and so on, none of these intermediate states is a bad state, right? So none of these S0, S1, SF is a bad state. That is, in none of these states does the head of the snake hit the or is in the same position as any of the bricks. So I hope the solution to the search problem is clear. See how carefully we define the problem to say what is the sort of solution we are interested in. Finally, I may also like to have a preference, and the preference is that this sequence of actions, the sequence of actions that I had, like A0, A1, that I got in my solution, that should be the smallest possible. So I get the, so essentially I would like to get a solution which is the smallest sequence of such actions, such that each of the actions are connected by a transition relation, connected by the transition relation. None of the intermediate states that you land up by doing these actions is a bad state. And the final state that you land in after taking the final action is a goal state, right? So this is how we describe a search problem or a solution to a search problem. Now, if you try to understand how does this, the state space or the set of all states in this game look like, you can actually arrange it as a tree. Like for example, you say that I start with my initial state, and then I can take all my actions. Like I can, from this initial take, I can decide to take the left action, I can decide to take the right action, I can decide to take the up action, I can decide to take the down action. For each of these actions, I can run my transition relation, and I will end up getting some state, right? Now for each of these states, I can again run my transition relation and again take all possible actions that I can take. And then I would end up landing in another state, or another set of states, right? And I can keep on unfolding this tree forever. So I'll get like big subtrees for each of these cases. For each state, I will take all possible actions such that they are connected by the transition relation, and doing so I'll keep on unfolding this tree, right? So this essentially shows how the state space is organized. It says that how are different states related, like which is the neighbor of each state and so on. Eventually, one of these states or one of these sequence of states would lead me, or the sequence of actions for that matter. For instance, if I take the, from the initial state, if I take the left action, and from here let's say I take the down action and some other actions, eventually one of these paths or one of these sequence of actions may lead me to the goal state. So now I can abstract out this game as a computer science problem. I can essentially say that what I need to do is I need to search on this tree to find a path which is nothing but a sequence of moves to take me from my root, which is the initial state, to a state, to a node, which is a goal node. And how can you do this search? Now, because we know it is a tree, you have already learned a lot of tree search algorithms. So you can apply any of these tree search algorithms to search this tree, right? So you would have already learned about, say, depth first search or breadth first search and so on. So you can use any of these search algorithms to now explore this state tree such that you can reach from the root to one of the goal nodes. So the state space, as you can now see, is a tree. To formally define, if the nodes in the tree are nothing but states, and the edges in these trees are actions, and I say that some node, Si is the parent of node Sk, if there exists, if I take from Si, if I apply my transition relation, I end up getting Sk. right? So, and now because you know that it is a tree, you can use your tree search algorithm to search for this, search this tree to find the node that you are interested in. This is the node that has the goal. Now let us look at how we can uh, describe our tree search algorithm. So our tree search algorithm takes a problem which contains the initial state, the whole state space, that is set of all possible states, the set of actions, the transition function, the set of all bad states, and the set of all goal states. Begin with, what we will do is we will say that let us start with exploring the. So I will start with having a list L which will contain all the set of states I am interested in exploring. So to begin with, we will start with the root node S0, and we will see that how does the tree unfold if I start with the root node. So I keep on doing this till my list is not empty. As a first step, I will look at this L and I will try to select some state from it. Select one of the states from it. So currently my list has only one state, but later we will see how this particular list can grow. What we will do is we will look at this list and we will try to select some state. Rather, let me try to put it as a list, and we will try to get one of the states from this list to explore further. What node we select from this list is what we will spend a lot of time on, and this is what is referred to as the search strategy. How we do this search, so this will essentially dictate the performance of the algorithm. For now, let us assume that somebody tells me that this is the node you need to select. So we have this select function which gives me a node. Then how do we run this algorithm? After we have selected some node to explore, I take all possible actions that I can take and I unfold this tree. For example, for now I have this state S. I look at all possible actions that I can take from this particular state. Doing so, try to find out for each of these actions, I will try to find out which is my child state. Like for example, let's say I end up getting C1, end up getting C2, end up getting CM. So there is a small technicality here, that this TA can be something referred to as a partial function. So what it means is it is possible that some state, for some state, for some action, there is no next state. So this is possible, and if you think of the game, you can think of the case where, for example, your snake is already at the leftmost edge of the game canvas, and if you press left, right, so then the snake does not have any place to move, right? So this is the situation I'm talking about. Like for example, this is the situation and my snake is already on the leftmost edge, and in this position I give an action which tries to move left. So in that case, I do not have a next state. I do not know what to do next, because if you move next from here, if you move left from here, it will take you out of the game canvas, and that is not allowed, right? So in some cases, it is possible that for a given state and an action pair, you would not have the next state. For every possible pair for which the next state is possible, we will check if any of them is a goal state. If this is a goal state, or this is a goal state, or this is a goal state. If any of them is a goal state, I then simply output the solution and I am done. If none of them is a goal state, then I check if any of them is a bad state. Let's say I say that, let's say none of this is a goal state, And let's say I find out that this is a bad state, this is not a bad state, this is not a bad state. For every state that is not a bad state, I add that child back to the list, right? So initially my list was only S. After doing this expansion or doing one iteration of this loop, my list becomes, so S is removed from the list, and I end up getting the children such that none of the children is a bad state. So C1 is a bad state, so I don't put it, but I do put C2, C3, Cn. And then again I go back to the loop and I try to again pick the next state from this list. Again, my select function, whatever it is, will define which is the next state I select, and that is the particular node I'll pick to grow. Right. So if you think about it, so you start with state S1. I expand it into all possible children that I could get by running the all possible different actions that I have. If some of them is a bad state, I just stop it there. For anything that is a good state, I expand it further by rather like out of the all the remaining states, I select which is the next state that I want to pick. For that particular state, I pick a set of actions, take the set of all actions, and then again I expand it to all possible children that I can get for this particular state. Again, from this set of states, I see if anything is a bad state. If not, if something is not a bad state, let's say this is a bad state and this is not a bad state. In that case, again I use the select function to define which is the next state I want to pick, and I keep on unfolding this tree till eventually I hit this particular case. That is, I land in a state that is a goal state. So I hope this tree search algorithm is clear to all of us. So now let's try to see how do we have this select, how do we design this select function? Because I have not said how to design this select function. We just said that somebody just gives you which node to select. So the first strategy that I can pick is something that you guys already know, perhaps, is referred to as the depth first search. So what depth first search does is it always selects the very first state, right? So essentially it will, like for example, if you get S is the initial state, S0 is initial state, and let's say I have C1, I have C2, and so on. Let's say this is already a bad state, I eliminate this, but C2 is a good state, so it will select the leftmost state or the first action which gives me a valid state. On this, again I do the expansion, again I eliminate my bad states, and again I select the first action that gives me a valid state, and I keep on exploring exploring like this. So the way DFS is exploring this tree is it is going deeper down the tree rather than broad, rather than going like exploring the siblings in the tree, right? So this is how my select function does. So what does my select function do here in this case? The select function simply selects the first child which is not a bad state. Now, if you want to understand what is the memory requirement of this state, of this particular algorithm, this is nothing but Bn. So B is basically the branching factor, which says how many such actions do we have, how many times how many children, what is the maximum number of children that a state can have, and M tells the depth of the tree, right? And you can easily see that it is order of Bn. Why is that? Because like you can see that for every state, I will expand it into B children because there are B possible actions. Again, for the next child, I'll have B possible children. Again, we will have B possible children and so on. And we'll keep on having it for the m depth of of the tree. So overall we will have m times uh, b number of states that I need to save. So that is the size of my list L in the previous algorithm, right? So we will need to maintain that many states to run this algorithm. So that is the memory requirement of this algorithm, or the space complexity of this. Now there is a small caveat. What happens when the tree has infinite paths, right? So there is always a set of actions I can keep on repeating. What happens to depth first search in that case? In this case, the depth first search can let us, because it is always picking the first child, the depth first search can keep on picking the first child for every node, and this can go on forever. So the depth first search may not even be able to terminate. It may not be able to return anything at all. So one way to avoid such problems is to use a different select algorithm, and this is again something that you guys already know, is referred to as the breadth first search. So what does breadth first search do? So breadth first search essentially takes explores all the children. If there is a bad child, it removes that. For every other valid state, it again explores all the children. Again, it removes the bad states, and again it explores all the children. So essentially what it is doing is it is going in a breadth first manner. So it is exploring the siblings before going down through the children deeper into the tree. So let us try to find out this guy's memory requirement. So in this case, what is happening is at every level you can have as many as b children. In the next level, you will, for each of these b children, you will have b more children, right? Each of these states will have b children. So in total we will have b cross b children. In the third level you can have b times b times b, that is b cube children. So if we try to add it up, the total number of states we might need to maintain is b for the root, b square for the first level, b cube for the second level, and so on. And if you sum it up, you will see that this is nothing but order of b to the power d plus 1. So this is a, so let us say that in all we have d levels, right? So this is d is the maximum depth of the tree. In that case, if you sum it up, you will see that it is nothing but b to the power d plus 1. Now if you compare these two, can see that a breadth first search requires a lot of more memory. In fact, it requires exponential memory as compared to depth first search. So now we are in a dilemma, right? Because breadth first search is great because it takes depth first search is great because it takes very little memory, but it has a problem that it can land into infinite paths. Moreover, it may not give me the best possible path, right? Because it keeps on exploring the path down the line. So let's say I get a solution through a long sequence, it will return me that, even if the second action could have given me a solution in just one step, because it always picks up the first path, the leftmost path. So this does not give you an optimal answer. It does not give you the uh, shortest possible solution. However, it takes very little memory. On that, on breadth first search, because it is doing things in this breadth first manner, it is always trying to find out what can I reach in one step before going further. And if any of them is a goal state, I just stop there and there. So that is why I, in this case, um, so the it will always give me an optimal answer, but the memory requirement is very, 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 very high. So what do we do? So there is something also known as a uniform cost search. I will not get into it, because if so, uniform cost search says that, so what is a cost? Remember what is a cost? The cost is the price I pay for taking a transition, right? So this essentially says that, like every transition in our snake game, we are increasing the length of the path by one. So that is my cost. So minimum cost means that I want to get the shortest possible such path. So uniform cost search says that it is possible that in this tree, not all these paths have the same cost. So I will always pick the child to explore, which has the minimum cost. Um, as for if everything has the same cost, then uniform cost search is nothing but the breadth first search. So let's not talk about it too much. So right. So now let us try to see, if we implement these strategies, let us try to see how do they play out in our snake game. So if we have this depth first search, it keeps on exploring uh, one direction end to end. If we run breadth first search, it keeps on exploring a lot of paths, and you can see it is hardly making much progress, right? And after some time, you will see it gets really boring because it keeps on exploring the same state again and again. So none of these techniques really work for us for the snake game, and we have to do something else. But at least these two strategies tell us that actually there are different parameters that I might have to weigh my strategies. The first parameter here is something referred to as optimality. So optimality says that if I am able to get, for my snake game, the optimality will be the smallest path or the smallest sequence of actions, right? So it says that I would say I have got the optimal solution to the snake game if I have been able to take the smallest sequence of actions, which takes me from the initial state to the goal. So the first question is, does my algorithm guarantee optimality? That is, whenever it returns a solution, does it always gives me the best possible solution? As you can see that uh, depth first search is not optimal. It may not return me the best solution, but breadth first search is optimal. It will always give you the best solution. The second is completeness. Completeness says that even if I, so let us say that there does exist a solution in this tree. Will the algorithm be able to always be able to return me a solution? So you will see that there are some algorithms which may not be able to return you a solution even if a solution exists. So completeness says that if the search is complete, that if a solution exists, it is always able to return that solution. The next is termination. Termination says that are there possible executions where the tree can go on forever? It may not even come out. Right? We saw that problem with DFS. The DFS search may not even terminate, but a breadth first search, if the goal exists, will always terminate. The next is complexity, and there can be time complexity and space complexity. Time complexity says that how much time or how many steps do I need to solve to do this search to reach the goal, and space complexity says that how much memory would I need, which is essentially the size of the list that we had, the list of all pending states that we had. So, as none of the algorithms that we saw worked, neither depth first search or breadth first search worked, we have to do something about it. And we saw that it's very difficult to pick one search strategy of DFS or BFS amongst them. One very clever strategy to combine both BFS and DFS is something referred to as iterative deepening. So the idea is that, let us say you are at the root node. What you should do is that you try to do a DFS, but you do a DFS till a specific threshold, let's say DT. So let's say you expand it to some child, you expand it to some child, you expand it to some child, expand it to some child. Once you hit D, Even if there is a possible expansion that you can get, you will not expand. So you will go back and you will explore the other part of the tree. Again, you will explore the other part of the tree, which might explore more. You keep on doing that till you reach, till you have explored the whole tree, till this level dt. If you have not still found the solution, if the solution is still not there amongst any of these states, what you do is you increase this threshold to a larger dt. So you increase it to say that okay, now you can go to dt1, right? And then again you start expanding till you hit this new node and you finish this search till this. So what you are doing is you are iteratively deepening how much of the tree you are searching. So you can clearly see that it solves one of the problems with DFS, right? So even if there is a infinite depth path and the solution could have been here, original DFS would have gone forever. But now, because we are trimming the search at a depth, I will essentially go back and I will be able to hit this other node, right? Before if I don't get it, we'll deepen further. So iteratively deepening improves my DFS because it allows me to now work with trees which may have infinite paths. The second thing is that as compared to BFS, it is actually much more memory efficient because within a depth we are actually doing BFS. We are not doing a BFS. So I do not need to maintain all nodes at all levels. So the question is that how do I figure out how deep this threshold should be? How do I pick these thresholds? And oftentimes you can actually use some heuristics to find out. So oftentimes there are properties among your state space. You know that from one state, what is the maximum distance another state can have, right? So that is again problem specific. But if you can come up with that, that is what is referred to as the diameter of the state space, then that can be used to design what is going to be my iterative deepening thresholds. The other very interesting search is referred to as bidirectional search. What bidirectional search does is essentially it, let's say it has a initial state and let us say it has a goal state, say G. It starts doing search from both these directions. So it starts expanding the S0 into differential realm. At the same time, it goes backwards from the goal and starts expanding G into its predecessors. What could be the state before you reach G? You again expand this into all possible states and expand this into all possible states. So you keep on expanding them like this till some branch from the backward P, from the backward search from G hits upon the forward search from S0, right? So if we hit upon a state which is like common to this particular search and also common to this particular search, then we have been able to actually construct a path from the initial state to the final state. And essentially, we have got a solution. So this is a very, very clever thing to do. But and one interesting reason to do that is if you think about it, like if we had only done the forward search, then the whole search that I would have to do from S0 would essentially look like this big circle, right? But now we are essentially exploring two small circles, so we are exploring much less number of states, then exploring a lot more number of states in this big circle, right? If we had only done this forward iteration. However, one catches that in this case you will need to have the function t inverse, which essentially allows me to do this backward search, because the forward search you expand by applying t. So you take s0 and apply t to get to the next state. For the goal state you have to go backwards, you have to go to its predecessor, and that is why you have to apply t inverse, the inverse of the transition function. And for many problems, coming up with this t inverse might be problematic. What about in our problem of the snake game? In the snake game, t inverse is not that problematic, right? Because like if I take a left move, then my snake goes left. Sorry, if I take the left move, my snake goes left, and t inverse is nothing but doing the right action, like moving it right, right? So there are inverse actions for us, like the inverse action for the left is right, and the inverse action of right is left. Similarly, inverse action of up is down, and the inverse action of down is up, right? So for our particular case, computing t inverse is pretty easy. So uh, those are some possibilities. But one of the problems that we were seeing in our last animation was that we could see that the search was hardly progressing. I mean, it was not, it was moving very, 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 very slowly. So the dots were showing how fast the search is moving. And if you could see, it kept on shuffling between itself, right? So so the problem was that when you have a tree search, what you're doing is that, let's say you have expanded this particular whole tree. When you are getting S5, you might again expand the whole tree all over again, right? But if you see that S5 is already here, so this S5 is nothing but this S5. And whatever subtree you will get here is nothing but the subtree you would have anyway got here, right? So why do this redundant work again? So what graph search says is that if I've already visiting a certain state, don't visit this subtree all over again. If I have, so I need to remember which is the states I've already explored. And if I've already explored a certain state, and you detect that after getting here, you get to S5, and you see that I have already seen S5, in that case, you completely remove this state from your search. You do not expand along that search any further. So this, you can see, can have exponential savings in exploration, and that search can get much better with this. So if you think about the algorithm has changed very slightly. So now what we are doing is, after we set a node to expand, we see if this particular state has already been visited or already been explored or not. If it has already been, if it has not been explored, then I mark it as visited and I continue. If it has already been visited, it has, like, if it has not visited, then I mark it as visited, and I continue, and I add the children of that node to the tree. If it has already been visited, I do not do any of that, and I simply go to the loop all over again and select the next. So in essence, what it is doing is, it is not exploring any node that has already been explored in the past. Another very interesting way to do search is to use something called beam search. So what beam search does is that, let us say that you have this list, and this list can grow very, very large, and we can see that in breadth first search, this list can grow exponentially. What beam search says is, let us not maintain this whole list, because very likely the whole list is not going to be very useful. So it uses a function to find out what are good nodes in the tree or good states in the tree, and we will try to, I will discuss more about how we can come up with this measure of goodness. But it has some clever function of telling me that which are good states, and whatever are not good states, it removes all the good states. So it maintains the k, some k best states. So you can have the beam search with a list size 10, you can have beam search with list size 2, and so on. So a beam search with list size 10 means that I will always maintain only at most 10 elements in this list. A beam search with a size 2 means in this list can at most have a size 2. Everything beyond 2 I will remove. I'll prune out. I'll remove from the. The problem is that this now starts becoming incomplete. You may lose out completeness because whatever we remove may have been a good state. I mean, we do not know. I mean, we are just estimating that something is not good, but in reality, the reality could have been different. So it is possible that it can actually give you a path which is not the smallest possible path. At the same time, of course, you can see that by the same argument, it may not even give me the optimal path, right? Okay, so sorry, I messed up a bit. So it may not give me the shortest path, which means that it may not give me the optimal path, and it may also sacrifice on completeness because it is possible that whichever path could have led to a goal, I am removing that. So that is possible. So now let us try to look at some animations of these different search techniques. So you see now with graph search, DFS is much faster. It is able to do some exploration. The exploration is going much faster. So the bubbles are showing how the exploration is moving. However, you can see the depth first search is not optimal. See such a long path it took. It took such a weird path to all the way to the apple, though there was a more direct path. See, it is taking such a weird path to the apple. It is taking all unnecessary moves and taking a very, 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 very long path to the apple. Right? So it has, see, for the average path length is almost 51. I mean, every step almost took a path length of almost 51 steps. This is breadth first search. Breadth first search, you can see, is again much quicker than the tree search. And see, it is always taking a very short path. It's taking a very, very short path to the tree, to the goal. However, it is exploring nodes on both ends. So you'll see that it is exploring a lot more nodes, but it is always picking the best possible route to the apple. The path length is only 14 from 50 plus in case of depth first search. Now this is breadth first search with a beam size of 10. So it means that I only maintain at most 10 best elements. And you will see a very interesting thing here. Just remember the last step that the snake is taking. Just try to remember the last step in this animation. So if you see the last step, it actually took the left side. It moved from the left side of that structure to reach the icon. Now we have a beam search with a size 2. So you can see the beam is much smaller. It is exploring a lot less number of nodes and it is much faster. But see the last step, it's taking a different route. It is going on the right side. Right? So essentially this is what we meant by when we say that it may not be optimal. So it took a longer route to the goal than when we were not using beam search. The previous search algorithms actually assume that I do not have any knowledge of my problem. In many cases, that you can actually look at the problem and you can come up with some structure about the problem or some functions over the problem which can actually help you search more efficiently. One such measure that you can have is something what I refer to as the measure of goodness of a state. So it says that how good is a state or how likely is a state to reach the goal in in a quick path, in a small number of steps. If we assume that our algorithm has access to such a measure of goodness, I can do something referred to as an informed search. So whenever I'm not using these problem specific knowledge about the state space, we call those searches as uninformed searches. And those were the searches we had seen till now, like breadth first search or depth first search or bidirectional search or iterative deepening. These are all uninformed searches because they do not assume that I have any knowledge about my state space. However, if I assume that I have some knowledge and I can actually quantify how good is a certain state, then I call those algorithms as informed search algorithms. So these are informed searches. And one such informed search we've already seen, which was this beam search. So the beam search was actually using the measure of goodness to retain the k best solutions in my set, right? And discarding everything else. So now let us look at some more informed search algorithms. So formally what we will do is to maintain this measure of goodness, we will define a function f that sort of approximates how good that function is. So, and this function is something we will refer to as an evaluation function, right? So we will design an evaluation function as f, which given a state. So if on f, if I give a state, it will give me the goodness. It will tell me how good that particular state is. Now, how you come up with this f is completely up to the designer of the algorithm. The algorithm designer will have to come back and design this nice algorithm, this nice approximation of goodness. And then what we will do is that we will, instead of choosing just any state, we will use something called a best first search, and we will try to select a state which appears to be the best state as per this measure of goodness that we have defined, right? I understand that this is just an estimate. This is not the reality. Nobody knows the reality. So this is just an estimate of as to how I think the good the state is, right? So to measure the state of goodness, we essentially will have something called, we will take the help of another function called the heuristic function. The heuristic function again uses a problem specific knowledge, and it tells that how far is a state from a goal state. Right? So it will say that if I am it at a certain state S and I have to reach the goal state, how much, how far I'm from it. So how much do I have to traverse to reach from S to G? So the first informed best first search that we will use is referred to as the greedy best first search. So what the greedy best first search does is it actually uses the heuristic function, the evaluation function, it sets just to the heuristic function. So it says that I will always pick the node which is best as per as the given heuristic. So let us think about what could be a good heuristic function for our snake game. So let us say that I am at a certain place. My snake is here. So this is my snake, and there are some bricks here, and there is my goal here, right? So what is a good estimate that I come up with? Can I come up with? Because I know the goal, I do not know that there are these bricks here, and I'll have to go around it, and those are very complicated things to figure out. One very simple estimate of goodness is to say that what is the Euclidean distance between these 2 points, right? Again, understand that this is just an estimate because in reality, I cannot take this path because there are bricks which is blocking this path. But still, it is a good state. It's still a good estimate, right? Because if I had some other state S prime, then that is surely further than this, right? So if I had a choice between exploring S prime and S, then I should surely start with S because S looks to have a smaller distance. So in our case, Euclidean distance, that is ignoring all the bricks, seems to be a good heuristic function, right? It just the Euclidean distance to the goal give me a good estimate that how much I might have to go till I reach the goal. So there is an interesting caveat. So if you set your uh, heuristic function h as a zero function, that it always returns zero, then our evaluation function, or rather I would say that I set my evaluation function to the uh, to the cost, that how much I have. So essentially, let's say I am at a certain state, and I refer to as to okay. Let me just confuse you. Let us not worry about this at all. I'll talk about this later, or maybe I'll talk about it in the discussion. I think it's digressing from the story. Right. So yeah. So now we know that how to design this heuristic function for our state. We can simply take the Euclidean distance and use that to figure out which is the state I should explore next. The advantage of this is that it is very fast. However, one problem of this greedy search is that it may not be the most optimal thing to do, right? Because it selects it only selects a state on the future promise, but it ignores the history. So think of this case that I had this initial state S0, and this is my goal G. And I have two states. I have a state S1, which has a very small distance, let's say 2 to a goal, but it has already covered 1,000 steps. On the other hand, I have another state, let's say S2. It has only covered, let's say, 10 steps, but it has a larger size, let's say 5, to reach the goal. So my heuristic function, or my greedy best first function, would say that okay, between S1 and S2, I see this guy has to only travel 2 distance, this guy only has to travel 5 distance. So this seems to be better because it has to only travel shortest distance. But then the total cost of this path is nothing but 1,010. However, if I had taken the one which has a longer distance, the longer heuristic distance, which is 5, then my total path length could have been much, much shorter, which is just 50. So the problem was that the greedy search completely ignored the history. It completely ignored that how much did I had to already travel to come to these states. Because if I've already traveled a lot more, then so any path which has really traveled a lot, I should completely discard it from the search anyway. Because it is very less likely that it will eventually give me the shortest path. Because it has already traveled so much. So it being the shortest path, chances become less and less. So we should design a heuristic which is based on both the past cost and the future promise. So which is this is the heuristic and this is the cost function. So the cost function says what is the true cost of coming to this particular state from the initial state, and the heuristic function says that from the current state, what is the estimate of reaching my goal. So we should actually try to cover both of these. So A star search is a search which uses the heuristic evaluation function as nothing but a sum of the cost function and the heuristic function. And it will avoid the sort of problem that we discussed in the greedy best first search. So, right. So we will see that. Right. So we will see that A star search. So as you can see that the greedy best first search may not give you the best possible path, because as we saw that in this case it will return me a path with length 1,002, though there was a path of length 15 available to me. However, under certain conditions, we will see that uh, the A star search will always give me the optimal solution. it will always give me the optimal solution when the heuristic function is such that it underestimates, rather I should not say underestimate, it is does not over approximate. So what it means is that the cost of the heuristic function is less than the true cost to the goal. Whenever that condition is met, my uh, A star search will always give me the optimal path. So any such heuristic, which is always optimistic, that is, it always gives you a brighter picture. It tells you that the actual heuristic cost or the estimate is smaller than the true cost, is referred to as an admissible heuristic. Right? So just to repeat it again, so whenever it is the case that my heuristic function, just to draw it again, so whenever it happens that my heuristic function gives me an estimate, say h of s, which is always less than the true cost, the true cost to the goal, then I would say my HS is an admissible heuristic if it happens for every possible state S. So if for all S I have that H of S is less than or equal to the true cost between S to G. So now I can state it as a theorem. So the theorem says that A star search always gives me the optimal solution if HS or the heuristic function is admissible. So I think I'm maybe a little short of time. So there is I have a proof sketch, but I'll let me not go through the proof because so the intuition is very clear. The intuition is that because my depth first search or my A star search is, let me just give you the intuition why it is optimal, but let's not do the proof. So let's take the same case that we had seen earlier. Let's say there is S0 and there is G, and there were two states, S1 and S2. And I know that the total cost through S2 is actually is actually some cost, let's say C hat. So in this case, if you try to enumerate this path to G, because it is not an optimal path, the cost to this must be some C which is greater than C hat, right? And if it is the case, it is surely the case that, and what is this particular cost? This cost is nothing but C of that particular state plus H of that particular state. So that is clearly going to be greater than C hat, right? Because it is not the optimal path. And because that is the case, there must be some node which will be picked later, which can be picked only after this whole route. That is the shortest route, that is C hat has got evaluated. Right? So you should sit back and try to think why it is the case. So again, going back to the same example, I mean, if I had these two states, I had okay, let me just go back to that example again. So we had these two states. We had the path to path to S1, which is of uh, size 1000, path to S2, which is of size 10. So in that case, when I have to pick between these two states, between S1 and S2, the cost of S1 is nothing but 1000 plus the estimate to G. Let us say the estimate is even zero. I don't even care what the estimate is. In that case, the total cost of this path is nothing but already 1000, right? From S1 to pick G is already 1000. On this path, because my heuristic is an admissible heuristic, the maximum heuristic value that I can have at S2, the true path size is 5. So the at most the maximum heuristic value I can have is 5. It cannot be more than 5 because it is an admissible heuristic. That is why the total cost, no matter what, the total cost of this path can only be 10 plus 5, that is 15. Right? So you see that the evaluation function of S2, f of S2 is 15, f of S1 is, say, 1000 is already the cost, and let's say the heuristic cost is the minimum possible, it is even 0. Even in that case, it is 1000. So in this case, I will always end up picking S2 and go to the goal through the shortest path rather than taking this longer route while through S1. So one important thing to note here is that I said that A star tree search is optimal whenever the heuristic is admissible. However, if I use a graph search, then it is not guaranteed to be admissible. So A star may not be optimal if we use an A star graph search. And I would like to use a graph search because, as you saw, that graph search is much, 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 much more efficient than doing a tree search. So why is that? Why is it the case? The reason for this is that every single state in a tree, there may be multiple instances of the state on different paths. Like, for example, let's say I start with S0, and let's say I have some state S5 here. I can also have some state S5 here. And when I'm doing a tree search, I will expand this also separately, and I will expand this too separately. So it is surely the case that if you hit upon the goal state here, this particular path P1 will have a longer distance than this particular path. So these two trees are identical, right? Because they are starting from the same state. So surely this particular path is shorter, right? So even if I have got a goal with a longer path, because I will still explore S5 again when I hit it the next time in the tree. That is why I still have the hope, or I'll still end up getting the shorter path. However, in graph search, what will happen is if I've already got this longer path and I hit upon this particular instance of S2 again, I will not even explore it, because that is what graph search is. Graph search says that if you've already explored a certain node, do not explore it again. And that is why we will fail to reach this shorter node. So if you want to understand formally what's going on is that, let us say that SP1, SP2 are these different instances of my state on the tree. So of the same state S on the tree. So like, for example, I had this S5, so I am calling it S5P1, and I am calling this S5P2. So in this case, when I explore it, I end up exploring the first path, that the state I explored, let's say, is S5P1, right? So my cost for CS is going to be the cost of, let's say, this is okay. So right. So essentially, the cost to some P. So the notation is a little weird, but okay. So what it says is that let us try to find out, among all these different instances of the same state on the tree, which of this is explored first, and take that cost as the cost of the state. However, when we get to optimality, what we would like to have is that I would like to have the minimum of these instances as the cost of this node. So this is what the algorithm does. This is how it will set up the cost. And this is in graph search. This is a graph algorithm. This is what it will pick up as the cost, and this is what we desire, what we really want for optimality. And it will be optimal, so only if the whatever path which explore first is actually same as the minimum path. If the path we explore first is greater than the minimum path, we will end up having a non-optimal a non-optimal solution, like the case we got here. So this is so explored first was SP5, and the minimum of all these nodes was nothing but S5P2. And because these two are not the same, in this case, I will end up getting a non-optimal path. So this particular problem occurs if HS does not satisfy the triangle inequality. Um, and let me just illustrate it through an example rather than going into the details. So consider this particular graph. So let us try to run our graph search on this algorithm. Run the A star search on this algorithm. So what does A star search do? The A star search would start with S0, will start with this particular node. Then it will look at the cost of all its children, right? So it has two children. So the cost of the heuristic, the evaluation function cost of S1 is nothing but 1, which is the cost to reach the node, plus the value of the heuristic, which is 6. So this is 7. Cost of S2 is 5, which is the cost of the heuristic, cost of the actual cost to reach this node, and 1, which is the cost of the heuristic. So this is 6, right? So between 7 and 6, it will pick up this node to expand. Okay. So now what it does is, no, so now it has, so now my list will have which states? So it has S1 and S2. This had a cost of 7, this had a cost of 6. So it decides to expand on this particular node, on S2. So now S2 has only one child, which is G, and the cost to reach G is nothing but 9 plus 0, right? So now my list will have, so I will, so S2 is already explored. So I have S1 with a cost of 7, and now I have G with a cost of um, 5 plus 9, that is right. So 5 plus 9, which is 14. Okay, so okay, so now next what it does is it out of these two things, it finds out that I should pick this particular instance. I should pick S1 with a cost of 7. So now it picks S1, and then it removes S1 from the set, and it gets G with a cost of 14, and it gets S2 with a cost of 1 plus 1 is 2, plus the cost to reach the goal is 1. So this is, no, I think my solution has, so it is 2 plus 1. This is S2 will go with the cost of 3, and I will end up taking 3. No, I think, I'm sorry, I think this particular solution does not work. I think I made a mistake in putting the weights. But essentially, but let me just give you an idea as to what is going on. So if you think about this particular edge, if you think about this particular edge, see what is the heuristic cost on this edge. The heuristic cost on this edge is 6, and the heuristic cost on this edge is 1, right? So it means that if I am at S1 with a heuristic cost of 6, if I take this edge which has a cost of 1 and I reach this S2, then I am able to reduce my heuristic cost to just 1, which is weird, right? Because I already had a high cost, I already took a new transition, and that lowered my cost. How can extending the path lower my cost, right? So this is, if such a scenario occurs, we say that this is inconsistent. So my weights went wrong here. I think the structure is fine, but I had to shuffle around the weights. Maybe I think I typed something wrong. Instead of 1, maybe this is 1, but yeah, I can tinker around with it, but let's do it later. Okay, so whenever you have such an inconsistency, whenever it can happen that taking a transition can reduce my cost, reduce my heuristic estimate, then I say that my heuristic is inconsistent. So if I have consistency, that is for every node. So let's say I have n, and my heuristic cost on n is h of n, and I take a transition to n prime through some t, and the cost of this is c. Let's say this is, let's say, on some action a. So let's say this is, the cost of this is c a n prime. So in that case, the heuristic cost that I get, h of n prime, should be greater than the original heuristic cost plus the plus this particular cost, right? So essentially it says that h of n prime should be greater than equal to the original heuristic cost where I started off with, or rather, yeah, I think this is more right. So essentially it says that my original cost that you had, h of n, that should be less than, that should be less than the cost that you incur plus the new heuristic cost that you end up getting. So essentially, it means I cannot have an inconsistent. I cannot have an inconsistent heuristic application. That is, it cannot happen that I have some h1 here, and I take an action of cost c, and I end up getting an h2 here, such that H2 is H2 is lesser than like H1 plus whatever you could have here. So that inconsistency is not allowed anymore. So I cannot reduce my heuristic cost by taking a new transition. That is what it means. So now you can actually prove this theorem that this A star search, A star graph search is optimal if my heuristic is also consistent. The good news is most of the admissible heuristics automatically give consistency. So it's a very tricky situation that you have to come up with where it is not consistent. Now let's think about our case. So what was our heuristic? Our heuristic was the Euclidean distance, right? It was Euclidean distance between two states. And why is it admissible? It is admissible because the actual path length must always be more than the Euclidean distance. So it is surely our heuristic of Euclidean distance. It's admissible. And why is it consistent? It is consistent due to triangle inequality, right? So the triangle inequality says that if I have a Euclidean space and I have 3 points, then the distance, this particular length, must be smaller than the length of this plus the length of this, right? So C must be less than A plus B, less than or equal to, right? Due to that, our heuristic is also consistent, right? So if we do a star graph search on our implementation, on our game, we should still get a uh, optimal solution. So now let's try to run uh, our game on these new heuristics, the informed algorithms. So this is the greedy search, and this is the A star search. So I will also show you some very contrived example where you will see that the greedy search can go so wrong. So see how long a path the greedy search is taking to reach the apple. But if I run the A star search, see what it does. See how clever it is. So how clever it is in figuring out the shortest path to the apple. So with that, I will end this session. But then the story continues. This is not the end of search algorithms. So there are other cases. Like for example, what if I have partial information about my? So I do not have complete information about the environment. So we only have partial information about the environment. So how do we do searches in those scenarios? What if the environment changes? What if the environment changes? What if the apple starts moving? Right after each step, let's say the apple also starts moving. So how do I design my search? Because I cannot plan the whole search and start again because by that time the apple would have already moved. What if the environment is stochastic? What if my apple moves, but my apple moves with a certain probability distribution, right? Say let's say it moves with say a Gaussian distribution with a certain mean and variance, right? What if my environment is adversarial, right? What if the apple is also clever and it tries to move in a manner such that it can avoid the snake? How can I design my how can I move my snake so that I can even catch the apple in such a situation, right? And now you can see it's a game. Now it's a game between the snake and the apple, right? The apple tries to run away and the snake wants to catch it, and we have to figure out how can we design a search in such a scenario, right? So the search algorithms, I mean, you can continue reading up more on search algorithms. So this is a very good book to look at, and if you are interested in reading more about the algorithms I have discussed and more algorithms that you want to read up, do look up this book. And I will actually just show you some animations of all the search algorithms in that contrived space that contrived maze that I had shown you earlier. You can see how do they look like. And with that, I'll close my session and I'll be happy to take questions.
Participants, if you have any questions, you can raise now.